on cloud. We are a cloud robotics summer school, and now you will see us moved to companies to iRobot, and he will tell us about his experience there. So thank you, Ben. You can start.
Great. So I'm Ben Kehoe. I'm a cloud architect at iRobot. My title recently changed from Cloud Robotics Research Scientist, which is one of the buzzwordiest titles I've ever heard. I got my PhD from UC Berkeley in 2014 with Ken Goldberg. And my work then was on a few different things through my PhD. I worked on collaborative tasking for unmanned aerial vehicles, which is sort of a different kind of cloud for robotics. And that was a focus on highly autonomous systems rather than swarm robotics, where you have a lot of low capability robots acting with good communication in concert. This was a lot of high capability robots with bad communication between them. But then I shifted gears into what happens when you do have a good connection. It may not be completely reliable, but it gives you access to vast amounts of computing power, vast amounts of data, connections to humans, and that's sort of where we got into the cloud robotics piece. I did projects with Google on using image recognition for grasping, other grasping projects around using sampling to improve grasps under uncertainty, things like that. I then joined iRobot, and I've been there since 2015. And with there, and this is where we'll go into the serverless aspect, iRobot's production cloud infrastructure supporting all of our connected Roombas has no virtual machines and no containers in production. It's all completely serverless, relying on primarily Amazon Web Services. So compute happens in AWS Lambda and other services there. As part of that, as part of my work in the AWS community, I've been recognized as an AWS serverless hero. So I think, there will be some people here who have built a robot from scratch. Probably fewer people who have built a robot from scratch for work and not just for fun. And probably nobody here who has built a robot from scratch for work, where the work was not actually about how to build a better robot. Sort of on the flip side of this, everyone here probably has worked with a robot that you didn't build, but that had some flaws that you wished you could make better. However, I would be willing to bet that nobody here who's in that situation would be willing to build that robot completely from scratch in order to fix those frustrating flaws in those robots that you're using to accomplish research on something that isn't just how to build good robots. Now, this wasn't always the case. We used to build robots, and I say we, this was long before my time, in the early days of robots, where to do anything in robotics, you had to build a robot. You couldn't just buy one. If you were researching swarm behavior, right, which is high-level robotics, you had to design and build your own swarm robots. You had to know mechanical engineering, you had to know electrical engineering, and today you can just buy a bunch of cheap drones on Amazon, and with Prime shipping, 2 days later, you're already doing your actual research work. Even if you're building a robot, you're probably buying standard components like motors and gearboxes and maybe 3D printing parts, so you don't even need machining experience. Now, sure, some people do need to get into building robots. A good example of this was the MIT Cheetah robot, which was how fast can we make a robot go, at the boundary of what we can build. And so they were, custom winding direct drive motors, because to go fast with a big-legged robot, you really need to design things all the way down. But this is a really special case, right? And the same thing happened in software as well. We used to write software for robots from the ground up, code on bare metal microcontrollers, drivers for our hardware, low-level controllers for our actuators, image processing for our cameras. But everything got better, right? As computer got better and cheaper, like think about all the uses the Raspberry Pi made possible. We could run Linux. We could run real-time Linux when we needed to. Manufacturers could provide drivers for their hardware. we're still writing networking, writing controllers, path planners, and so on. And then in the early 2000s, people started looking at how to make that better. So frameworks like Player Stage from Microsoft, Orca, and then ROS, which, as everyone will recognize, sort of won that competition. ROS came with networking solved, a framework for component lifecycles, standard interfaces for robotics information like images, poses, kinematics, point clouds, and had an ecosystem of components. So you didn't have to write your own driver, controller, image processing pipeline, if you didn't want to. If that was what you were working on, you could go make your own. But if what you were doing just used processed images, then you would just go use the image processing pipeline and use the output of that to do the work that you wanted to do. So that lets you focus on working on the part of the system that you were good at, that was what your research was really on. And then there was the PR2. You know, this was a while ago now, but people may remember this. It came with everything you needed to do robotics, right? Of course, it cost a huge amount of money, but at the time, it was the hardware, a bunch of compute, all of the ROS infrastructure needed to use the robot. And for the most part, it just worked. You'd buy this thing and then go get on with the business of pushing robotics further. There are predecessors and contemporaries that offered similar out-of-the-box simplicity or whatever, but the PR2 is really sort of the landmark in this space. And now one thing to note is that the PR2 actually shipped with two eyes on its head. You know, you can see that they're slightly different here. One of which was a camera, and the other was a texture projector. This is a custom 3D sensor, and at the time, you know, in 2012, 2010, that era, many people were building these custom 3D sensors to get point clouds out. But then the Microsoft shipped the Kinect, and it was $150, and it was a 3D sensor with an API, and everybody stopped building their own sensors, right? You could just buy one. The PR2, even though they had made this complicated head with a texture projector and a camera and everything, they shipped with just a Kinect bolted onto the top because that was easier and better. So we call these things that you have to do just to get working on your specific area of expertise, undifferentiated heavy lifting. It's heavy lifting because it's hard, it's a lot of work, and it's undifferentiated because when you do it, it doesn't put you ahead of everybody else, it just gets you to the same level, right? It's not the thing that makes you different, it's just table stakes. So this is stuff that you don't want to take on if you can help it, which is again why the PR2 was such a big deal, why ROS was a big deal, right? Solving these undifferentiated heavy lifting problems that everybody has, that's hard, and that nobody wants to do and shouldn't have to do. So now to shift gears for a bit, the same story is played out in the software industry at large, right? It used to be that when you needed another server, you called up Dell and you ordered one, and then it was shipped, took a week to arrive, and then you had to install it in your data center, give it power, give it cooling, provision it. Finally, you were up and running. And then that was weeks later that you now had the right software on it, that, had control of it, all of those things. And we got better at this with virtual machines. You could buy bigger servers less often and share them more easily, and even swap out who was using a server without much impact on them. But then came the cloud, right? And now instead of weeks, you just ask the cloud for a virtual machine and you're up and running in minutes, right? This was huge. And one of the things that gets talked about in this is this difference between treating virtual machines or pieces of software, whatever it is, as pets versus cattle, right? When you have a physical server that you own, you need to nurture it, you take care of it, you make sure that it's running. When something goes wrong with it, you fix it. And that's very much how we deal with pets, right? We take them to the vet, we give them names, right? Servers often had specific names. And on the other hand, when you have a herd of cattle, they're given numbers, and when one gets sick, instead of, taking it to the vet, you make meat out of it. And similarly in the cloud, with virtual machines, they all get, sort of anonymous identifiers And if one's not working, you just cycle it out. And then you go even further than that, and we start getting software as a service, right? This range from like full-fledged applications like Google Docs. Instead of being responsible for installing and updating Microsoft Word, you just use your browser and it gets better for you over time without your involvement, right? And at the other end is sort of web services that are components, building blocks. So Amazon S3 was one of the first of these. The simple storage service, binary object storage. It's not file storage exactly, not like Dropbox where there's a user-oriented user interface and file features, but simple get, put, delete, object. What you put in there is up to you, and what you do with it is also up to you. It was easy and cheap, and you only pay for what you use. And you didn't have to ask for more storage space, right? It's this sort of functionally infinite storage space in the cloud and, you know, bare bones, simple interface that works for all of those things. And so the range of software services continued to expand, but we still had code to run, right? You can't use services for everything you do. If there's a service for all of it, you wouldn't be doing something new. So your code has to run somewhere, and virtual machines were a lot of work. So we developed containers, right? Which let us package up code in a way that encapsulates sort of all of its dependencies all together, so that you know that it will run correctly in another place. But here's the thing about a container. You still own a lot of stuff inside the container, the operating system, the runtime for your code, any of these dependencies. So we developed platform as a service. Heroku is the classic example of this. Just give me your code and I'll put it on a server with the runtime and the OS, database connection. I'll upgrade all of those things for you over time, but you're still responsible for the scaling. You have to pick how many instances of this thing you need. And maybe you can tell me as Heroku, you know, when to scale up, when to scale down, and I'll look at the CPU usage or the RAM usage, right? That's a poor proxy for what you really care about, which is probably something like your user's request latency. So providers tried to push that forward, right? What's the way to bring your custom code and be able to manage both maintenance and scaling? When we need new servers, when the existing ones are handling too many requests. But what if each request got its own server, right? And to manage everything under the code, we have to shut the server down. If it's handling only one request at a time, we can just not send it a new request and cycle out that server. And so this model looks much more like, give me some code and I'll run it in response to an event in its own environment, subject to some time limit. And we'll call this functions as a service, right? And this is really just the result of trying to remove as much undifferentiated heavy lifting as possible from running code in the cloud. We call this approach, using managed services and functions as a service, serverless, and it's a terrible name. You know, I know many people who work in the serverless space, and nobody likes the name, and it's also losing meaning because as a useful technology, it gets applied to more and more things that are less and less like that. But we're stuck with this name. A better term, coined by Patrick Dubois, inventor of the term DevOps, if you're familiar with that in the industry, is serviceful. Because really, functions are a small part of the overall picture. You want the custom code that you're bringing to be a little bit of glue, the mortar between all the bricks, and the bricks are managed services, those things doing the parts of your application that you don't have to care about. So now, how does this mesh with, what's happening here, with robotics? So I want to now switch to my journey with serverless and iRobot. As I was finishing my PhD in 2014, I was working on a framework called BRASS. And the idea behind this was that roboticists have code that they want to share with other people. They have data that they want to share with other people. And that's traditionally been very difficult. You can, give them the code, but getting it running on their machine is often hard, and containers can help with this. But the idea behind this work that I was doing at the end of my PhD was saying, well, if you add a little bit of annotation to your code, can there be a framework that packages it up as a web service so that it runs somewhere and then people can just use that service rather than needing to get the code running themselves? And so I was working on that, containerizing robotics algorithms, things like this. And, something that I wasn't good at was, okay, well, how do you scale it out? How do you do all those things? And in late 2014, AWS Lambda came out doing the functions as a service thing, saying it can run some code in response to events. And I said, hey, this looks great. This is the kind of thing that I'm interested in. And then as I graduated, iRobot was announcing that cloud robotics was a focus area for them. And as a cloud roboticist, scale is the primary factor that makes things interesting. And iRobot has more robots than anyone else. So this was a natural fit. And so when I joined in 2015, this was prior to the launch of our first connected Roomba, the 980. And we launched with a full solution IoT cloud provider. So a service that did all of the things, firmware update, communication, authentication, all of those things. But we already knew before launch that it wasn't going to scale like they said it would, and wasn't really flexible enough to do the new things that we realized that we needed to do, like making an Alexa integration on that platform would have been hard. So we realized that we wanted to move off of that onto something that allowed us to control more of our own destiny. And to do that, we chose a service from AWS called AWS IoT to be the connectivity layer. But then that left us with how do we build the back-end functionality behind it, given that we haven't built scalable elastic cloud services before and didn't have people who were well experienced in that. So I looked at Lambda and the range of managed services from AWS API Gateway, SQS, S3, all of these things, and said, I think we can build this without ever having to learn how to make the scalable things because all of these services scale for us. And so we went all in on that we said, all right, great, we're going to need 30 of these AWS services to accomplish this. But if we make the Rube Goldberg machine, it's actually just going to kind of run itself. And so this has been incredibly helpful. And I want, an illustrative example here for this, which is to talk about Christmas Day. Christmas is our biggest selling season. And unlike our other big events, Mother's Day in the US, Prime Day with Amazon, right? All of those, Prime Day, we sell lots of robots, but then they arrive, not all at the same time, and not everybody opens them exactly when they get it. Whereas on Christmas morning, everybody who's bought a robot for Christmas opens them all in a small window of time. And so our traffic looks huge relative to our normal traffic. You can see here it's many times higher than our average traffic. And so in most companies, this would be, a major operational event, right? That much traffic coming in requires a huge amount of preparation that you have to think about how you're going to scale, and all of your systems are scaling out properly and everything. For iRobot, this is a non-event. That this traffic that's, at a daily rate 5 times higher, but reaches, close to 20 to 50 times higher at the peak, is literally hands-off keyboard for us. In 2021, this massive wave of new robots rolls in, and we had to do nothing. We literally didn't need to change anything, touch any part of our system, because all of the pieces of it scale for us. And it's hard to understate how powerful that is. That that not only, in terms of operationally, are we doing nothing, that our employees are relaxed, right? They're at home with their families, they're not worried about it. That we spend our time in December writing features to ship in January, not preparing for this event. So great, that's industry. How does this apply to you, right, in an academic setting? Research doesn't have these types of events. Sure, you do demos and things, but the point here is that we're not spending time making our system run. We're spending our time building features. We're building the application and making it do new things. And we only pay for what we use, right? In research, you don't want to waste time figuring out why something isn't running or paying a lot for computation that you don't have to. And serverless does this for you, right? If you build your algorithm as services and things, you can also potentially make them available to others as services, either freely or with one of the many ways that cloud providers let you monetize APIs, et cetera. So I want to talk about some of the challenges here in cloud robotics and how serverless helps. And then after, we'll talk about where serverless has its own challenges. So the first is skills. Roboticists are going to be specialized in robotics. It's already a full-time job for cloud developers to know how to build and run traditional cloud applications. It's even more work then when those applications aren't, a basic web app, it's something involving robotics. Serverless helps here by removing skills that can be abstracted behind a fully managed service. If you have a lot of events flowing through your cloud system, the traditional answer is going to be something like Kafka, which you have to set up on servers and you have to manage it. You have to figure out how to configure it. You have to do all those things. Instead, if you use a fully managed service, I work with AWS. There are services like SNS, SQS, Event Bridge. These things help process events or manage event flows. No one needs to have that skill set of setting up and managing those things. The APIs are relatively simple. It's relatively easy to understand, and it's fully managed, right? So that lowers the barrier to entry for a given cloud robotics project. It does, of course, involve a new set of skills, and we'll talk about that, that of building a serverless application. But that's an easier lift and one well-suited, in industry to junior developers. So it should also be a good fit for grad students, well-mentored undergrads, right, that are able to gain those skills relatively quickly so that they can then focus on their primary research tasks. So of course, when your cloud bill arrives for your latest test runs, it can feel like you're putting money through a shredder. If you're really good at resource utilization, you can be cost effective with traditional architecture. You can make sure that, your virtual machines are out there and they're running at full capacity when you're using them, and then you shut them all down when you're not using them. But if you forget and you leave it running for an extra 24 hours, all of a sudden you've got this big bill and you didn't get anything out of it. In theory as well, and people note this, traditional architecture has a lower per CPU cycle cost than a serverless equivalent, because the serverless thing, you're paying for this extra management that it's doing. But it's difficult in general to be very good at resource utilization. And even when you are good at it, it's a high overhead on your time. You have to be spending time being good at that. Serverless keeps your cost lower for typical uses, right? And you have to worry less about those surprise bills where you've forgotten about something. Now it's not true if you build a, infinite loop into Lambda and those kind of things. And of course, cloud robotics is not always a typical use case. We'll get to that. So we've all been in the situation where we're reading a paper that includes a link to some code, and subsequently you spend like an entire day trying to get that code working on your own machine, right? Docker was a game changer in this space. Its uptake in robotics was slow, right? Cloud robotics is sort of even further behind that curve, because not only do you have some specific code, but you have a whole system that needs to be running to handle these things. And so it's not a single binary, how can you be sure that their Kubernetes cluster is sufficiently set up the same as yours so that the pods will correctly run. So serverless eases this pain as well, because when you're using managed services, those are by definition the same across customers, right? That their usage of AWS and your usage of AWS, you're using the same things. And it's AWS's problem to make sure that those work the same. So as a baseline, right, containerizing your code is going to ensure easier reuse. So this is for that code, that's the things that you've specifically built. And one of the notes is, it's going to ensure easier reuse, not just by other people, but by the future version of you, right? That you work on a project for 6 months and then you set it aside, you go work on other stuff for 2 years, and then you get a grant that relates to that first one, you got to get that back up and running. If you've containerized it, if you've set this up, that's just going to run again. Now, maybe you have to update the dependencies. You got to do a bunch of stuff to get it running again, but you're starting from a very good baseline there. There's a caveat here, which is that functions as a service like AWS Lambda often either let you bring, sure, here's a full container and run the code like that, or as a zip file. And I actually usually recommend the zip file. And the reason is that the container then says, okay, all of the OS dependencies, the language runtime, all has to be inside that container, and you're responsible for updating that. With a zip file, I'm bringing, here's some Python code, and the provider is responsible for saying, here's the Python runtime, here's the OS under it, and that will get updated for me. So I recommend that in industry. That's really important when you have sort of ongoing updates, when you're running it in an ongoing fashion. In cloud robotics research, where it's more about this, it gets set aside and then picked up again, I'd actually say the container makes more sense, but that is something to choose between. But that's only your code. And as we said in serverless, you're using all of these different services to knit together an application. So what you need to do is do the same thing, but for all of the cloud services. And so this is called infrastructure as code, sort of the equivalent of a Docker file. It's a definition, it's a single artifact that defines your cloud application. And you can hand that artifact to the cloud, to a cloud service, and it will go make sure that that application exists as you have defined it. That makes standing up and tearing down the application easy, and it makes updating it. You change that definition, you give that to the cloud says, all right, I know how to go tweak these things to make it different. And that's much better than configuring it manually, or even than writing a script that uses the cloud APIs to set things up. Right? Again, it's this artifact that you can hand to other people that, again, can change over time. That you say, hey, I know I told you it was this, but now here's a new definition. And instead of them having to delete what they have, they can just say update. And you're not responsible for figuring out that complexity. APIs are important. So if you create well-defined APIs, especially using a managed API service, AWS has API Gateway, that's similarly helpful. It's essentially documentation, right? You're documenting the inputs and outputs through that API definition. And that, again, can help you come back to it later, share it with others, where they say, what do I actually need to put in here? And instead of that being, well, dig into the code and go look at the definition there, it's up front on an API definition that they can look at. And you go one step further and you say, well, okay, I could provide these artifacts to people so that they could run it on their own, and that's good because they then pay for that. But if you have collaborators, if you have users, or you just want to make it, you've released the paper and you want to make it as easy as possible for people to try out, to reproduce your results, all of those things, you can actually use these managed API products, which have, API key management, rate limiting, all of these things, to say you're actually going to provide that as a service so that people can try it out without even having to set it up themselves, right? That then lowers the barrier to entry for other people reproducing your results, for sharing it with others, and all of those. So I've painted a pretty rosy picture. Everything should be serverless. It's all great. I want to talk about some of the places where it breaks down. So as I mentioned, right, it removes a lot of skill sets that you have to have versus traditional architectures because you're doing fewer things. But it is a whole new skill set. And this matters more, I think, for people who have a lot of experience with cloud applications because it's unlearning the traditional mindset of saying, okay, well, I have to set these things up and I have lots of control over what's happening, to a new one which says, okay, I'm going to try and find managed services that accomplish my needs, but I'm going to make it so that I'm going to deal with the fact that they don't always do 100% of what I need to do. That's much easier to learn when you're brand new to it. But also it helps to have someone who's experienced at it leading junior developers into that space. So again, just pointing at an undergrad at AWS documentation and saying, figure out how to do it, it's not going to work well. High performance computing, this is something where, again, resource utilization tends to be done better. And so those per CPU cycle costs can come back to bite you. There are projects that have looked at this and said, there's one called PyRen, like WREN, from that also came out of Berkeley. And that was saying, how can we actually decompose code so that we can run it in a giant compute graph on Lambda and have that be, again, the per CPU cycle cost is higher, but we also know that it runs for exactly as long as we need it and no longer. And so we're not owning this large amount of HPC infrastructure. It's more managed, all of that kind of stuff. So if you're doing a lot of HPC workloads, serverless may be less useful for you. GPUs are currently not really a solved thing for serverless. A big part of that is that there isn't really a standardized interface into that. That a virtual machine can just have an abstracted GPU device. So if you're doing processing that requires a lot of GPUs, AWS Lambda is not going to help you there. You still want to approach it serverlessly, so you have your GPU workloads running in virtual machines or containers somewhere, but everything surrounding it is managed services. So just because you have to go back to using, God forbid, a Kubernetes cluster, doesn't mean that you should default all the way back to everything should be running in Kubernetes. So keep that in mind. The last one is ROS. ROS 2 has come along finally to say, to use in industry, there's all these things about ROS 1 that don't work. It's got no security, any of those things. And ROS 2 has come along and solved those problems. What it hasn't solved well is multi-tenancy. So how do you have multiple different robots that can talk to the cloud through ROS, but can't share, that the cloud can process these things separately, but in a way that won't mix data between these two robots? That's generally something you need for a cloud robotics system that looks like something that could get used in industry, but isn't something that ROS supports well. So I often see that sort of cloud robotics ends up with a bridge to the cloud where it's ROS sort of locally, and then when it crosses over, it's either moving into a different protocol like MQTT where there are those capabilities for separation, or it's establishing a single connection out to some compute that's single tenant for that robot, which again then doesn't have the scalability and cost advantages that the cloud could provide if that multi-tenant capability was better there. So those are some of the challenges. Vendor lock-in gets talked about. I'm not sure how much in academia that people care about. In industry, people are like, oh, what if I have to move off of AWS onto Google? No one ever does that. So it's not actually a real threat. It's something that people worry about a lot that doesn't actually happen in real life. which is sort of the thing. I think also, in sort of research situations where, well, I built this for AWS, and the next thing I could build for Google is probably true. If you have a lot of partnerships, like if you're like, oh, I could get this big grant from AWS or Google, and I'm applying to both, and I need my code to work on both, then maybe you're in a situation where you want to step back and say these managed services are different between AWS and Google. So I'm going to rely mostly on containers for this stuff, so that when that grant comes through, I'm going to be able to go with whoever's giving me the money, is sort of a thing. But don't worry about it for its own sake unless you have a specific situation that you can't be vendor specific. So that's the whole thing. We are at time. I don't know if we have time for any questions, but I'm happy to respond to that. My email is also, I don't know if that's in the thing, but I know Angelo has it, so can provide it out.
Thank you, Ben. Can you hear us?
Yes, I can hear you.
Hi. So if you have time, first let's.
Sure.
Time for questions from our future experts in cloud robotics. I think you need to. If you come closer, it's better. Yeah. So we have one of the participants coming to ask a question.
Sure.
You can just start already.
Okay. Hi, Ben. Can you hear me?
Hello. Yes,
Hi.
I can.
Thank you very much for the inspiring talk. And actually, I have a question when you talk about the challenges, and I noticed that you didn't mention the delay and the real time of the cloud computing. And of
Sure.
course, you already started. I mean, 7 or 8 years ago, you said that real time is research focus. And after these years, how do you think of this real-time cloud? Is it still a challenge or it's already solved?
Sure. I think, well, there are two things here. I mean, the latency of the cloud is a cloud robotics topic all its own, right? And so I think that's not specific to the serverless, non-serverless divide, right? For every 100 miles you go, you get a millisecond of round trip latency. And so it's going to be hard to do 1,000 hertz control in the cloud because of physics. However, there's lots of solutions for this, right? That the cloud can do sort of extra heavy processing and return a policy back to the robot rather than telling the robot what to do in an individual situation, right? So hand back something that can be processed locally at a high rate. So you can sort of, have that meta processing. The other thing then is if you do have very latency sensitive requirements for your cloud robotics system, that's again going to push you away from serverless because being managed services, there's just more things going on inside them so that they do more complicated stuff for people, but is less specific to your application. So if you need the absolute minimum latency, you're going to be looking at running containers or virtual machines or whatever it is, right? You're also then going to want to look at pushing that compute more towards the edge. So, on AWS, there are regions, and there are, in the US, for example, 4 public regions. But there are also now these like local zones. And so instead of these 4, there's, 8 things, and you can get, a local zone in Los Angeles, and you can get a local zone in Boston. And so if I'm iRobot and I have a robot in Boston, as we do, that's where our headquarters is, and we wanted a system that was extremely low latency, but not actually in the room with the robot, going all the way to Northern Virginia for the US East 1 region is a long ways for that latency, but the local zone in Boston is going to be closer and have lower latency. Now, again, that requires more undifferentiated heavy lifting. Those local zones have fewer of the nice things that remove that work from you in the cloud. So hopefully that answers your question.
Yeah, thank you very much.
Thank you, Ben. Any other questions? Okay, so thanks for your participation. Thanks for the early time for you. And I think we can just wish you a good breakfast, I guess.
Great, thanks so much.
So thanks again for participating in this.